Welcome once again to another talk of the Discovery Seminar Series. My name is Isabel Rebollido. I am a postdoc here at Space Telescope working with Marshall Perrin, and today I have the honor of being the chair in substitution for Mireia Montes, who has recently left us for her next adventure at the Canaries. As you might already know, the aim of the Discovery Seminars is to showcase the work of the postdocs of the Space Telescope and the Johns Hopkins community, because early career researchers have been disproportionately affected by the COVID-19 pandemic due to reduced travel and networking opportunities. And on top of that, the large community of international postdocs have also been separated from their families and loved ones, which has significantly affected their work. With these talks that will take place till the end of July, we only have 2 more sessions left. We want to provide a platform for these postdocs to show their results to an international audience of astronomers, so feel free to share the information of the series with any of your coworkers or collaborators that might be interested. Please, at the end of each talk, feel free to ask questions. You can use the raise hand button that should be under your People tab. I will call them and you can unmute yourself to speak at the end of the talk, or you can, at any time, write your questions in the chat. And when the speakers are done, I will read your questions out loud for you. So without further ado, I would like to introduce our first speaker today, Ramona Augustin. Thanks, Ramona. She's one of the organizers of this series, so thank you so much. She got her PhD from the Aix-Marseille University in 2019 for her thesis, where she spent 2 years at the European Southern Observatory headquarters in Garching, Germany, and 1 year at the Laboratoire d'Astrophysique de Marseille, LAM, in France. During this time, she worked on characterizing the circumgalactic medium of damped Lyman alpha host galaxies and creating mock observations of circumgalactic emission for various instruments, including the balloon-borne UV spectrograph Fireball 2 and the optical and near-infrared IFS Harmony in the ELT. She joined a Space Telescope in Baltimore in fall 2019 with the FOGGIE simulation team, where she's now working on characterizing the small-scale structure of the circumgalactic medium, combining high-resolution simulations and observations of lens quasars. So you can just go ahead, Ramona. You know you have 25 minutes. I will let you know when you have 5 minutes left, and everyone else, you're very welcome to write your questions in the chat.
All right, thank you very much, Isa, for the introduction. I hope you can see my slides now.
Yeah, you can go ahead.
Awesome. Yeah, thank you so much for the introduction, and thanks to everyone attending my talk. I'm going to present to you today my work that I've been doing on studying the circumgalactic medium, and particularly focus on how we're trying to constrain the small-scale structure of the circumgalactic gas. Now, before I talk about any of the details of my work, let me quickly define to you what I mean when I talk about the circumgalactic medium. So we know that galaxies reside within this kind of extended halo that is filled with gas, and all of the major gas flows into and out of the galaxy are happening and mixing in this volume that we call the circumgalactic medium. These processes directly affect the galaxy's evolution, as fresh material that's being accreted onto the galaxy from the cosmic filaments can feed the galaxy and can trigger star formation. And at the same time, feedback processes within the galaxy, such as star formation, AGN, supernovae, all of these processes can drive outflows of metal-enriched gas from the galactic disk into the halo. And actually, these outflows can go on different pathways. So some of it might leave the halo completely and enrich the intergalactic medium with metals. Some of it might slow down and remain as diffuse gas clouds in the halo. And some of it might actually mix again with the inflowing gas and re-enter what we call the galaxy's baryon cycle and go again into star formation processes.
We're having some interference with the audio. Maybe you can speak close to your computer, because I think it's like you're just a little bit too faint for your microphone.
Okay. If I speak a little bit louder, is that better?
Yeah, I think that would be better. Thank you.
Okay. I'm very sorry for this.
You're good. Thank you.
All right. So yeah, all of these processes directly affect the galaxy's evolution, and therefore it's very fundamental for us to understand what's happening in the circumgalactic medium. However, typically, when we study galaxies in the universe, what we're seeing is the light that's coming from stars, not from the gas. So I'm illustrating this to you here by showing you two videos that are made from the FOGGIE simulations that I'm going to talk about a little bit later on also. And on the left-hand side, you see what the stars are doing in this galactic halo. And on the right-hand side, it's the same halo, but you see the gas component. So you see a lot of different structures in the gas, like fairly constant inflow filaments, first the outflows, filaments connecting the different satellite galaxies that you would all be missing by only studying the stars. And I hope the videos are not too choppy coming through. So for this talk, I want to focus on three main questions to be addressed. First of all, let's find out how the gas is distributed around galaxies, and then ask, can we somehow observationally constrain the gas structures in the CGM? And also, can we somehow maybe distinguish inflowing gas from outflowing gas once we do detect gas in the CGM? So for that, we first of all have to look into how we can study gas, and particularly circumgalactic gas in general. For this, we have two main methods. One is to study the gas in absorption, and the other is to map it out in emission. Now, ideally, we would like to do the latter. Just take a picture, similarly as we do for stellar light, and just map out the gas structures around galaxies. However, the example that I'm showing you here on the right-hand side has two caveats. First of all, this is a group of 5 galaxies. It's not a single galaxy that is spanning this huge Lyman alpha halo. And Lyman alpha is typically the brightest line that we can observe in the universe. Metal lines, which might trace different states of the gas around galaxies, are much fainter, and observations of such are much rarer. And also observations of single galaxies and their extended halos are rare and typically limited to small extents beyond the galactic disk. To make predictions of the emissivity of the circumgalactic gas and its observability with current and future facilities, I've created mock observations from Ramses simulations. I've combined outputs from this cosmological simulation with a cloudy ionization model to calculate the flux for a range of emission lines from each gas cell to create these emission maps that are shown here on the left-hand side. As you can see, Lyman alpha is by far the brightest line, and also it's particularly strong in the central parts of the galaxy. As you go out in further away from the galactic disk, or look at metal lines, you can see that the expected flux is significantly fainter, and therefore also more difficult to observe. We have used these emission line maps as input to instrument models for different facilities. And the one example that I want to show you here is a 5-hour observation with Harmony, which is an optical and near-infrared eye view that's going to be a first light instrument on the ESO extremely large telescope. As you can see from the comparison of the dots, which are for Harmony, with the crosses and X's, which are for Symphony and MUSE on the VLT, this instrument is going to be a lot more sensitive to these faint fluxes. And we actually expect to be able to detect the faint gas of the CGM. However, at the same time, also resolving individual gas structures on small scales will remain challenging also in the future. So this is maybe not the way to go for the moment. So let's focus on the other method that we have to study gas in the universe, and that is absorption. So for this, we look at a very bright background source, typically a distant quasar, and then any gas that sits between us and that quasar will produce an absorption line in the spectrum of the quasar. If that absorption line is fairly strong, we will assume that it's maybe arising close to a galaxy due to the increased gas density close to galactic disks. And it will pose a good target to follow up and identify also the host galaxy, such that we can draw a connection between the gas in the circumgalactic medium with its host galaxy. This field actually has been revolutionized over the past years by the use of integral field spectroscopy, because now we can take images of a quasar field where we know that there exist some observers, and then every pixel in that image is a spectrum. So we can use those to identify emission at the same redshift as where we find an observer. And especially MUSE, with its large field of view, has been very useful for this. And very often we actually find more than just one counterpart galaxy for a given observer. In some cases, we even find entire groups of up to 11 galaxies, as shown in this example here, that are connected to a single absorption system, which makes the entire study a little bit more complicated. Now, the strongest observers that we know of are the so-called damp Lyman alpha observers. And because they are so very strong, we think that they must arise very close, actually, to the galactic disk. And since they are so close to galaxies, we typically find one galaxy that is connected to the absorption system, such that we can draw one-on-one connections with a galaxy and the gas in its surroundings. If we have a large enough sample of such systems, we can investigate scaling relations between galaxies and their immediate surroundings. And what we find, for example, is that the mass metallicity relation for galaxies also holds for gas in the outskirts of the galaxy if we correct for the impact parameter at which we're measuring the observer. So basically assuming a negative metallicity gradient into the outskirts of the galaxies. We also find an apparent anticorrelation between the stellar mass of the host and the measured H1 column density in its environment. At the moment, we didn't have enough data points to make this a strong conclusion and fit the relation. But if this relation holds true also for larger data sets, it would imply that there is an evolutionary trend where more massive galaxies deplete their surroundings more effectively of neutral gas through feedback processes and heating up the halo than lower mass galaxies. Now, all of these studies are very useful in order to understand the connection between galaxies and their immediate surroundings on a physical and average sense, but it doesn't hold any information on the spatial structures of the gas that we are probing in absorption. So how can we go forward to do this? To study the spatial structures of the gas that we are seeing in absorption, I've proposed to observe lensed quasars with the integral field unit MUSE on the VLT. And I also got some time during their science verification run for the adaptive optics mode, which helps to resolve the individual quasar images. So for those of you who are not super familiar with how gravitational lensing works, any massive object in the universe, typically galaxy clusters or very massive galaxies, bend the light that's coming from behind them on their way towards us. So they act in the same way as a glass lens would. If the background source is very close to the center of the lens on the line of sight to us, this distortion can become so strong that the light ray is actually split into several light rays. And what we then see are multiple images of the same background source. So you see here in the example that I've been observing, the lens galaxy in orange, and then the four white dots are 4 images of the same quasar in the background. Now, this is very useful because if any gas cloud sits between the lens and the background quasar, then we can probe this gas parcel through 4 different sightlines and look at the spectra of these 4 images individually. So we've observed this with MUSE, and this has been a pilot study, so we didn't really know what to expect, how many observers we would find along the sightline or not. But we find 2 magnesium-2 observers in this data, and I'm going to introduce you to them a little bit individually. So the first one we find at a redshift of 1.4, where we find a fairly strong magnesium-2 observer towards image C, which is this one. And then if we look at the spectrum of the other images, we don't actually see anything. Maybe there's a tentative detection in image B, but it's definitely not significant. To give you an idea of the spatial scales, these always depend a little bit on the exact geometry of where the gas sits between the lens and the quasar. But at this redshift, the distance between image C and A1 is around 1.7 kiloparsecs at this observer redshift. So this means that this gas parcel shows a fairly strong variation in absorption strength on less than 2 kiloparsecs. We also find a second system, which is quite a bit different. It is overall weaker, but it is detected in all 4 images. Of course, we might be detecting different gas clouds that just happen to show similar absorption strength. But if we assume that this is one homogeneous extended gas cloud, then it extends over more than 6 kiloparsecs, which is the extent that is spun by the 4 images at this redshift. For the second absorption system, we also detect a counterpart galaxy in our MUSE field of view, for which we detect O2 and can calculate the star formation rate. And since this is a well-studied quasar field, there's also a lot of archival HSD data that we could use to identify the galaxy, get its photometry, and determine its stellar mass. And now, while these systems are very interesting in themselves, they seem to be fairly different in nature. The one very, very compact, the other kind of extended. And we want to understand this a little bit better. So for this, we are now making use of simulations. For this comparison, I'm using the FOGGIE simulations. And I'm not going to talk about the details of this simulation, but what you should keep in mind is that where normally cosmological simulations always under-resolve low-density regions in the universe, particularly the circumgalactic medium, FOGGIE applies a forced refinement scheme to get also very good resolution in the circumgalactic medium. So these that makes these simulations ideal to compare to data where we want to understand structure in the CGM. So we pick a halo from these simulations at the same redshift as one of the absorption systems. And the halo that we're picking is slightly more massive and a little bit more star-forming than the counterpart galaxy that we find in our data, but still similar enough to allow for comparison. So what I'm showing to you here on the right is a magnesium-2 column density map of exactly that halo, which is cut at the detection limit of our MUSE data. So that explains the many wide regions. They're still magnesium-2, but we wouldn't detect it in our data. What you see here is that if you looked at the central part of the galaxy or also the satellite that's coming in here, you would get fairly high magnesium-2 column density. That's not what we're measuring here. What we're measuring here is between the red and yellow part. So if we look only at this kind of range, we see maybe 2 distinct types of features. We see these very clumpy and compact objects, and we see diffuse gas clouds that have this filamentary structure like here. This becomes interesting once we compare this to the radial velocity map of the halo, which is shown here on the left with red being outflowing gas and blue being inflowing gas. And you can easily see that these clumpy features line up with the outflowing gas from the galaxy, and these diffuse filamentary features line up with inflow filaments into the galaxy. Knowing this, we can now go back to our data and make a comparison. So I'm showing you here again the magnesium-2 column density map, but with slice through the radial velocity map in the background for comparison. So let's put a circle here. This circle spans around the region that is also spun by the 4 quasar images. And if we would shoot 4 sightlines into this area, we would arrive at a system that looks fairly similar to what we're measuring here on the left-hand side. If we do the same experiment and shoot 4 sightlines through this inflow filament, we arrive at an absorption system that looks fairly similar to what we're measuring here on the right-hand side. We've done a bit more of a quantitative analysis for this in the paper also, but for this presentation, I'm only showing you the visual comparison. And so knowing this, we can now ask the question of whether we're measuring here maybe an outflowing gas clump, and on this side, maybe we're measuring an inflowing gas filament. This is, of course, interesting, but it's still only one case study, and we would definitely need more such systems and also better theoretical models to make stronger conclusions on this. To go forward, I'm now asking the question, how do we actually expect the CGM small-scale structure to look like theoretically, and how does it then translate into observables, especially towards several sightlines, as we can get them from these lens quasar observations. So for this, I'm using again the FOGGIE simulations, and I'm showing you here a density map of a halo at redshift 1. You can see again the galactic disk, which has very high densities, and then you see all of these various structures in the circumgalactic medium around it. We can zoom in to one patch here, which is roughly 10 on 10 kiloparsecs. And what I'm working on at the moment, so all of what I'm showing you now is still preliminary. I'm working on a method to extract overdense gas features in the circumgalactic medium, defining small-scale structure purely on their density, and then only later on looking at other physical properties that these structures have, and also at their observable properties. So let's see what we find if we extract these kind of small-scale structures from the circumgalactic medium. We find that CGM structures overall are dense, cool, and metal poor with respect to their surroundings, which you can easily see from these panels here, where I'm showing you in the upper panels the CGM patch that we just zoomed into. And then on the lower panels, I'm showing you the same quantity, but what is only coming from the clump that we are extracting now. So you see the density here, metallicity over here, and temperature over here. We can also ask how this translates into observables. And what I'm showing you here is an H1 column density map, where again, I'm showing the full halo patch on the right-hand side, the clump only on the left-hand side, and in the middle, what would be left if we extracted the clump from the circumgalactic medium. And you can see two things here. First of all, the cool gas absorption lines, such as H1, have a very high spatial variation on kiloparsec scale. You see the color bar here spans 8 orders of magnitude, and you have all colors represented in just this tiny patch of the circumgalactic medium. We also find if we take all of the clumps that we're finding together and see how much of the column density comes from within those gas structures versus outside of it, that actually a large fraction of up to 70% on average comes from these tiny gas structures that take up a percentage or less of the volume along a given sightline. We can also look at the metal lines, and I'm showing you here the example of silicon, and look at the different ionization states of silicon now. And we see that the low ionization states, like silicon 2, most of it actually arises from within this clumpy structure, again, similar to H1. But as we go to higher ionization states, for example, for silicon 4, which we could detect along the same sightline here, and actually also even at the same velocity maybe, but it originates from a different part of the circumgalactic medium. It does not originate from within the clump, as you can see in the lower panel here. Only very little silicon-4 actually comes from this clump. Most of it comes from the gas around it, actually. And this is something to be kept in mind when taking observations and comparing different ionization states, that you're measuring along the same sightline, that they're actually probing different parts of the halo. So now let's go back to the questions that we asked in the beginning. And the first one was, how is the gas distributed around galaxies? So from the simulations, we think that we have this hot diffuse gas halo that hosts all of these cool, dense gas structures within it. And can we observationally constrain those gas structures in the CGM? I've shown to you how we can use lens quasars to constrain the absorption variation on certain spatial scales to get a constraint on the gas extent. And can we distinguish inflows from outflows? Well, this is a very open question, and there are various ways of how people are trying to address this. But I've shown you here that, at least from a pilot study where we combined lens quasars with high-resolution simulations, we found that there could be a potential correlation between the absorption variation that we're measuring in the data and the radial velocity of the gas that we're probing. So I will just leave you here with an illustration of my main takeaway point, and I'm happy to take your questions.
Great talk. Thank you, Ramona. Yeah, I'm not an expert in the field, but this all sounds fascinating. If people have questions, again, you can raise your hands or you can send the question to chat while we wait for people to chime in. If I can ask, because I think all of our minds are in the same place right now, what do you think James Webb can add to this? Are we going to have observations to test these simulations? What's your take on that?
Oh, yes. Yeah, definitely. I mean, the high resolutions of James Webb will definitely help with this. James Webb also has an IFU, which will be definitely very interesting to study more lens quasars also at higher redshifts to use for these kind of studies. So yeah, I think there will be various ways to go forward, also to identify host galaxies of known observers in more infrared, so higher redshift universe. I think there's a lot of potential there.
Sounds great. Yeah, looking forward to all of that, those studies. Yeah, it seems that we don't have any questions. So I know this talk will also be available on YouTube. So if you have questions about the talk, reach out to Ramona. And we're just going to move on to the next speaker, Matilde Mingozzi, who is also an organizer of the series. Thank you, Matilde. So she received her PhD in March 2020 at the University of Bologna in Italy, in collaboration with the Acetri Observatory in Firenze, Italy, under the supervision of Giovanni Cresci and Filippo Manucci. Then she moved to Padova for a postdoc at the Padova Observatory, working with Bianca Puglianti and the GASP team. Since November 2020, she has been at Space Telescope in Baltimore, working with Beth and James and Alessandra Aloisi as part of the Metals in Galaxies group, MINGO. Her main project at the Space Telescope is about the Glassy survey, of which today she will present some new results. Matilde's research interests are mainly related to probing and interpreting the physics and properties of the interstellar medium, feedback and outflows in different galaxy types through the use of a spectroscopy, both in the optical and the ultraviolet. So Matilde, you know how this goes. You can share your screen. You have 25 minutes. Ramona was just in time, so I didn't have to tell her, but it will let you know when you have 5 minutes left. Yeah, go ahead.
Okay, thank you, Isa, for the very nice introduction. Can you see my screen?
Yes.
Great. Okay, so hi everybody. So as Isa was saying, today I will talk about the work that I've been doing in this year and a half, more or less, that I spent at Space Telescope. And so I will talk about the UV interstellar medium diagnostics in local redshift analogs with Class C. And this work I've been doing this work in collaboration with the people that you see here and many more with the Class C team. So let's start from a general overview of the topic. So this is a cartoon of the cosmic timeline that highlights the most important periods in cosmic time, starting from the formation of the first objects during the Dark Age, and then the period of the epoch of the reionization, where ionizing photons escaped from these first objects, reionizing the universe, and then you can see the galaxy growth till the shape, till the form that we know they have today. And one of the big topics. Open topics of astrophysics is what properties characterized these first galaxies during the reionization, and how did they reionize the universe. We will have to wait JWST, and so we will have soon more information about these to have detailed insights on the physics of these high redshift systems. But observations of low redshift analogs of these galaxies can pave our way of understanding what happened during the reionization epoch. Of course, it's not easy to define a high redshift analog, especially because actually we don't know exactly how galaxies look like during the reionization. What we know is that the first galaxies must have been characterized by more extreme properties with respect to the local universe. In fact, from studies at high redshift that had been done in the past decade, we know that galaxies at high redshift are strongly star-forming, they are metal poor, with other ionization fields, with a significantly stronger emission line, as you can see also from this plot on the left, and they are characterized by higher and higher specific star formation rates, and they are also more increasingly compact and with low stellar masses. So we know all these characteristics. So these are the characteristics that we have to look in local objects in order to consider them local analogs of these high redshift systems. Another piece of this frame introduction that around the project that I will introduce soon is about the importance of rest frame UV spectra. Indeed, rest frame UV spectra can provide a unique window on massive stellar populations, chemical evolution, feedback processes, and also reionization, especially because they are accessible at all redshift. Indeed, in the local universe, we have HST, and so we can measure the UV from HST. Then moving towards slightly higher redshift, we have the rest frame UV, we can measure the rest frame UV through optical observation, through ground-based optical and infrared observatories. But at redshift higher than 6, we will have the infrared wavelength covered by JWST will reveal the rest frame UV in the reionization galaxies. Indeed, there are already some examples of very redshift galaxies where you can see the main UV emission lines. For example, here I'm reporting the case of a galaxy at 7.7, where you can see the Lyman alpha or the carbon-3 emission lines, or for example, this galaxy at redshift 6, where you can see the carbon-4 or the oxygen-3. So all of these are very important UV emission lines. The thing is that in order to use them to understand the conditions of the interstellar medium of these systems, we need to properly calibrate them before. To do this, we need a survey of local star-forming galaxies that can be representative of the high redshift universe, in order to study how these ISM diagnostics work. And for this, I want to introduce you to CLASSI, that stands for the Coast Legacy Archive Spectroscopic Survey, that at the moment is the largest survey with the full UV, with the full rest frame far UV spectral coverage from 1200 to 2000 angstrom, with a very high spectral resolution and high quality spectra. And in particular, class C is highly representative of the redshift universe for the broad range of properties in terms of stellar mass, star formation rate, specific star formation rate, metallicity, ionization parameter, and density. You can see this very well, for example, in this plot, especially in the left panel, taken from the class C presentation paper from Berg 2022. That was out just a few months ago. So you can see that the class C galaxies that are represented by the purple dots, they span all over from stellar masses from 10 to the 6 to 10 to the 10, but they are significantly shifted at higher star formation rates, consistent to higher redshift systems, with respect to the turquoise and blue line that represent the local universe. And also class C targets are characterized by very high specific star formation rates and by high oxygen 3 oxygen 2 line ratio that are an indication of very high ionization, and also are probing higher densities with respect to the local universe. But the most important thing of class C is the UV coverage that covers basically from the Lyman alpha till the carbon 3 emission lines around 1900 angstrom, more or less, because class C puts together 3 COS gratings, the G130M, G160, and G185, and while works that have been done in the past years tend to use only one of these gratings, so basically having access only to a reduced part of information and not to all the synergistic for UV science that instead you can do if you put together all this wavelength range, including the study of the stellar continuum and thus the massive stars and all the emission lines that can give you different informations. For example, from the helium-2 you can have information about the number of ionizing photons, the oxygen-3 are temperature indicators, the carbon-3 are density indicators, and then there are all the studies that you can do with the Lyman alpha. And before class C, only 2 galaxies in the archive had all this information, while now we have 45 of them. Moreover, for class C, we have also optical spectra that we collected for all the sample, putting together information from different instruments, from SDSS, LBT, MMT, and also from integral field spectrographs such as VMOS, KCWI, and MUSE. And we are sure that we can compare all of them without worrying about systematics too much, because and we studied this in a recent work accepted in APJ from Arellano Cordova, and if you are interested in this, you can go and look at the paper. And so basically, what we did in order to provide to the community a UV toolkit based on these redshift analogs that will be able to investigate the interstellar medium properties of the redshift universe, we investigated the main UV emission lines that are listed here. Here you can see how many galaxies with signal to noise higher than 3 have these UV emission lines, comparing them with the well-known optical diagnostics, in order to see how UV diagnostics compare to them, and to see if it is possible to create a only UV-based toolkit to investigate density, temperature, metallicity, ionization parameter, and also the main source of the ionization. So the last piece of all this introduction is about H2 regions and star-forming regions. So this is an image of a nebula of a star-forming regions. You can see the glowing of UV photons that are coming from these very massive stars that are ionizing the surroundings, and with their winds they are creating a cavity within the region. And you can see that you can see in different colors different emission lines, such as the oxygen 3, H alpha S2, because star-forming regions are stratified. You can also appreciate this from this figure that is a bit more complex, and I will drive you through this. So this is taken from Berg 2021, and so basically star-forming regions can be are standardly parameterized with the 3 zones, a low ionization, intermediate, and a high ionization region, because very far from the ionization source, you will have ions such as the sulfur 2 or the nitrogen 2, and so you can use these to measure the density, as 2O2 to measure the density, and to measure the temperature you can use the auroral nitrogen 2 with respect to the nebular one. And then moving towards intermediate ionization regions, you will have the S3, for example, that you can use as a temperature tracer. While for the density you will have, for example, the chlorine 3 in the optical, or in the UV you will have the silicon 3 and the carbon 3 emission lines. And then moving towards the higher ionization, you will have the argon 4 line ratios in the optical to measure the density, or the nitrogen 4 in the UV. While for the temperatures you will have oxygen 3. The oxygen 3 line ratio. This is one of the most used line ratio that is with respect to the auroral O3 emission lines and the nebular one. Daniel Berg 2021 introduced also a very high ionization that is characterizing high redshift analogs and high redshift systems because of their very high radiation fields and low metallicities. And because adding photons that are able to ionize the helium, and so this is basically the four-zone ionization models that is characterizing these star-forming regions. So what we did is to measure density temperatures and temperatures iteratively using PyNab in order to characterize the properties of the different ionization regions in the optical and in the UV. These are the first results that I'm showing you for the density. Also, this is a complicated plot, so I will drive you through it. Here you can see the density as a function of the metallicity. Actually, it's not very important what there is on the x-axis because we don't find important correlations with respect to the density and galaxy properties. What you have to look at is that the blue and the purple squares that are representing the low ionization tracers for density are measuring densities around 100 centimeters to the -3 in median, while for example, the orange pentagons that are the argon 4 emission lines in the optical that are tracing the higher ionization regions are tracing densities around 1000 centimeters to the -3. You can appreciate the difference with respect to the sulfur 2 densities in the bottom panel of this plot that shows basically the offset that you can see with respect to the low ionization region. The most important part of this plot, of course, is the right-hand side that shows the corresponding version for the UV tracers. Overall, the UV tracers, for which we have mainly carbon 3 emission lines that we can measure for more than 20 galaxies, have in median densities that are around 10 to the 4. So there is an offset that is more or less of 2x with respect to the low ionization density that you can measure in the optical from the sulfur 2 emission lines. Concerning the temperature instead, what we did was to explore how the hybrid optical UV tracer that compares the auroral line at 1666 with respect to the optical one at 5007 corresponds with the classical used oxygen 3 line ratio. Surprisingly, we found that the two are not so different. There are not major systematic effects major effects, with just a median difference of 1800 Kelvin between the two temperatures, with slightly higher values for the hybrid line ratio. This is surprising because the hybrid line ratio can be affected by many issues. For example, the fact that the lines are very far in wavelength, so there could be an issue in the attenuation correction, or the fact that we are using different instruments to measure the UV and the optical one. So this is very promising. You can use this line ratio to measure the temperature. and this could lead only to over or underestimation of metallicity in the range of 0.25 dex, so not a big difference. And this could be particularly important since the oxygen 3-1666 in our sample is 0.4 dex brighter than the optical auroral line 4363. Concerning the ionization parameter, in the UV, we don't know exactly which is the best way to probe the ionization parameter up to now, but in the optical, many tracers have been proposed. This is again a scheme taken from BER 2021, where for the different ionization zone, you can use a different tracer. For example, the sulfur-3, sulfur-2 line ratio for the low ionization regions, oxygen 3, oxygen 2 for the intermediate, and for the very high ionization region, the argon 4, argon 3 line ratio. It's interesting that if you use the prescription for BRAG 2021 to measure the ionization parameter for these three different tracers, you will get, as you see on the plot on the right, you will get basically a scatter of ionization parameters. And if you compare them with respect to the O3, O2, that is the mainly used tracer, basically, you will see that in general, the O3, O2 line ratio, you can appreciate this from the bottom panel. You can see that the oxygen 3, oxygen 2 line ratio gives ionization parameters that are more or less 0.5 dex higher with respect to the S3, S2, so with respect to the low ionization regions, and 0.5 dex lower with respect to the argon 4, argon 3, and so with respect to the higher ionization regions. We interpret this as a sign that in our galaxies there is an ionization structure that is particularly marked, as suggested by the work from BER 2021, since we are including high redshift analogs in our sample. So to give you an overview about this UV toolkit, what we are providing in a paper that we have recently submitted to APJ is basically a suite of UV-based diagnostic equations that we made comparing optical and UV diagnostics. And for example, for the densities, what I was saying you before is that the UV densities are more or less 2 dex higher with respect to the low ionization densities. And we also find a slight anticorrelation between the low ionization optical density from the sulfur 2 and the UV one that you can get from the carbon 3. So if for high redshift system you want to measure the low ionization density that you would get that you get for local systems, so if you want to compare your density with local system, you can use this equation to estimate that. For the temperature, we found that this line ratio is providing a reliable temperature diagnostics, and so you can measure directly the metallicity. And as I was saying, the metallicity is within a range of 0.2 dex with respect to the one that you would derive from the optical O3 line ratio, independently on the density tracer that you are using. Which is a nicely good agreement, let's say, between the two. But if you don't have a method to trace the temperature and so to directly trace the metallicity, you can also measure the metallicity using line ratios. What we found is a very nice correlation between the optical metallicity and the carbon 3 O3 line ratio. This is probably related to the relation that there is between the carbon to oxygen line ratio and the oxygen abundance. And even though there is a slight correlation also with the ionization parameter that you can appreciate from the color code in this plot. We also found that the equivalent width of the carbon 3 could be a way to measure the metallicity. The carbon 3 after the Lyman alpha is the brightest line in the UV, so this could be particularly useful, but there is a problem. That is that there is an anticorrelation, so the equivalent width, a lower equivalent width of the carbon 3 will correspond to a higher metallicity. But then if you go to too low equivalent width of the carbon-3, around 0.1, for example, you will have basically a drop of the metallicity because you will have also a drop of carbon. So there is an issue to take into account, but these are two equations among others that we provide in the paper from which you can measure the metallicity. Concerning the ionization parameter instead, we found that the most promising tracers are the equivalent width of the carbon-4 and the equivalent width of the oxygen-3. We measured the correlations with respect to the different tracers of the ionization parameter for the different ionization zone. In the paper, we provide all the equations. Here I highlighted only those with respect to the oxygen-3, oxygen-2.
5 minutes.
Okay, thank you. So, having said that, this is the UV toolkit for properties that we are providing. But what about the source of ionization of UV emission lines? So, of course, this plot that I'm showing you is taken from Felter 2016 and basically showing the spectral energy distribution of the incident ionization radiation and the different ionization species. So you can see that in gray there is the spectral energy distribution of NEGN, that can explain like very high ionization emission lines, such as the oxygen 4 or nitrogen 5, etc. And star-forming models instead at different metallicities, especially lower metallicities, can explain photon energies that are necessary, for example, to produce the carbon-4. So from different papers provided the photoionization models and shock models to try to explain the production of the necessary photon energy to produce these transitions. And these are some of the examples that we have. So on the left, you can see the classical BPT diagram from optical line ratios that is dividing AGN and star formation. From the paper from Felter 2016 that is focused on the UV emission lines, and in particular Felter 2016 proposes different UV BPT diagrams. This is one of them that compares the carbon-3 helium-2 with the carbon-4 helium-2 line ratios, separating very well star formation and AGN. Jaskot and Ravindranath in 2016 proposed the same plot, but this time to divide shocks and photoionization models, while Nakajima 2018 proposed another set of 3 different diagrams where photoionization models of AGN and star formation can be divided in a clear way using this set of lines to divide the parts of the plots, basically. So what we are doing now is to test how the classy galaxies compare with respect to this diagnostics plot. These are results in preparation. Basically, what we see is that in general the classy systems are located for the majority in the star-forming regions of these diagnostic plots, and this is expected since classy galaxies are classified as star-forming according to the optical BPT diagrams, but there are few outliers that lie in the AGN region according to some of the diagnostic plots, and we are investigating which properties of the ISM are pushing those points basically in those regions. And this is work in progress, so stay tuned. Last thing I wanted to say before jumping to the conclusion is something about the future perspective. So last year we got approved our HST observations that are planning to put together new observations and archival ones to perform imaging on UV emission lines for 3 classy targets. In particular, we will perform Lyman alpha, carbon-4, carbon-3, and helium-2 plus oxygen-3 imaging for for these galaxies that are characterized by very different shapes of the Lyman alpha and also different line ratios considering the other emission lines. This is very exciting because there are not many works that show UV imaging, especially of the carbon 4 or the carbon 3 emission line. Actually, there is only one at the moment that is showing the imaging of the carbon 3 emission lines. And so it will be very exciting to see if we can produce a spatially resolved UV BBT diagram with the information that we will get. The observations are ongoing, so again, stay tuned. And also we are collecting IFU data for our galaxies with also 9 classy objects observed recently last January with the KCWI in order to compare our cos spectra with our UV information with spatially resolved optical diagnostics to see how the distribution of optical properties is influencing our UV properties. So I hope that I've convinced you about the importance of rest frame UV spectra, and I just want to say that classy represents the largest sample of rest frame for UV spectra with high resolution for these 45 galaxies. If you are interested in learning more about classy, this is the web page and this is the MUSE portal where you can download the data, and you can download also Jupyter notebooks to deal with the data. And in the paper that we have recently submitted to APJ, we are providing a suite of UV-based diagnostic equations that will be useful in the JWST area to interpret the higher redshift systems. So thank you very much for your attention, and now I will take any questions.
Thank you so much, Matilde. Very nice talk. We do have a question in the chat already, so I'm just going to start with that. It's from Jason Tumlison. So he says, James Webb NIRSpec R2700 has a resolution closer to IUE than COS. Does this present a problem for applying these diagnostics at high C? Are the equivalent widths adequate?
So there could be, of course, an issue for the concerning the spectral resolution, because if the spectral resolution is not enough, you cannot maybe distinguish the carbon 3 emission lines, or you will have more problems in distinguishing, for example, for the carbon 4 emission line, there is a stellar contribution apart from the nebular contribution that we see. So for sure, if there is a spectral, if the spectral resolution is lower, there could be some kind of issues. But but since in classy we can avoid all these systematics, and so this could be useful to understand. This could be useful to understand better, to understand better also for the JWST observation. Sorry, I just I was thinking about this. For sure, I think that you could do is to compare our diagnostics with the lower spectral resolutions to see which is the difference, and this could give us information about how to use them. The other systems.
Great, thank you, Matilde. Anyone else has questions? If not, I think we can adjourn. Oh, yeah, I think we can adjourn. I would like to encourage everyone to join us for our next session on July 12th, where Maite Alfaro and Paul Bennett will be talking about galaxy clusters, the 2 different talks. Thank you so much for coming, everyone. If you have any questions for Matilde or Ramona, feel free to reach them, and see you next time. Thank you, everyone.
Thank you very much, everybody. Thank you.